Let's take a look at what happens to a material when we transfer energy either to it or away from it. To do this, we're going to look at what we call a heating curve. In a heating curve, we're going to track the temperature of a material as we add heat to the material. So let's start with a temperature of negative 18 degrees Celsius, and we're going to look at water. Now at this temperature, water will be in a solid state, and as we add heat to this, the temperature will increase until we reach 0 degrees Celsius. At 0 degrees Celsius, we now have the melting point of water, which is where the ice is going to convert from a solid to a liquid. As this is taking place, we continue to add heat, but the temperature no longer increases, and that's because all of the energy that we're adding goes into the phase transition of breaking apart the molecules in the solid into that liquid phase. And this will remain the case until we have melted all of the ice. Once we've melted all of the ice, now the energy once again goes into increasing the temperature of the liquid now. So once again, as we add more heat, the temperature now begins to increase. Now you'll notice the slope of the liquid line is different than the slope of the solid line. Let's clean that up a little bit. Okay, the solid line has a steeper slope compared to the liquid, and that's because in the liquid we actually need to add more heat in order to get an equivalent increase in temperature compared to the solid, and this is because of a property that we'll call heat capacity. The liquid phase has a higher heat capacity than the solid phase does. Once again, we can continue to increase the temperature though by adding heat until we reach 100 degrees Celsius, where we now encounter the boiling point of water, and once again we now have to use the energy not to increase the temperature, but instead to break the molecules apart from the liquid phase into the vapor phase. So we will continue to add energy until all of the liquid has been converted into a vapor, at which point we once again increase the temperature by adding more energy. Start. Let's now take a look at what's happening on a molecular level as we're adding heat or taking heat away from a material. So in solid ice, the water molecules will orient themselves in order to achieve a low energy state by orienting the hydrogen atoms so that they're in close proximity to the neighboring oxygen atoms in other molecules, and the oxygen atoms so that they're in close proximity to neighboring hydrogen atoms in other molecules. When we add heat to solid ice, if it's at the melting point, the energy goes into breaking up these interactions, okay, which then allows the molecules to move about freely. So to do this, we have to put heat into the system. In liquid water, we now have molecules that have more random orientations and are able to move around freely, but they're still in close proximity to one another. If we add additional heat, especially once we've reached the boiling point, this heat now goes into breaking these molecules far apart from one another, so they move into the gas phase where they're now far apart with very little interaction between the molecules. And once again, this is a process that requires us to put heat into the system. Now, if we go the other direction, if we allow these molecules to get closer to one another and to condense from the gas phase into the liquid phase, now we have these interactions forming, okay, so we go from very little interaction to these stronger interactions in the liquid, and we actually have heat that comes out of the system. Similarly, as we go from a liquid back to a solid, we go from this state where the molecules are close together but not aligned to the molecules aligning themselves into an optimal configuration, and once again we get heat coming out of the system. One way to differentiate between processes where heat goes into a system compared to when heat goes out of a system is using the terms endothermic compared to exothermic. So, for example, as we go from a solid to a liquid, as we mentioned on the previous slide, we said that we had to put energy into the system to break up those optimal configurations between the molecules. So we would term this an endothermic process, meaning that we have to add energy into the system to break up those interactions. Now, it's important to recognize that even though we're putting energy into the system, that's not increasing the temperature. That is simply going into causing the phase of the material to change from a solid into a liquid. Similarly, as we go from the liquid phase to the gas phase, again, we have to put heat into the system in order to break the neighboring molecules that are close together apart from one another. So that would also be an endothermic process. Now, we can also, in some cases, go straight from the solid phase to the gas phase simply by breaking the molecules in those optimal conditions straight apart into being far apart molecules, and we term this sublimation. This is what happens in dry ice. Dry ice is solid carbon dioxide, and if you put it out in just room temperature conditions, it will go straight from the solid phase to the gas phase, and that is also an endothermic process. In the other direction, if we have a gas changing into a liquid, we call this condensation, and this is a process that releases heat because you go from a higher energy state to a lower energy state. And then similarly, if we go from a liquid to a solid, we refer to this as freezing. And once again, this is something that releases heat. We can also go straight from the gas phase to the solid phase, and this is referred to as deposition. This is another process which releases heat. All of these processes which evolve heat are referred to as being exothermic. Now, one thing that's important to note is that when we talk about whether heat is lost or gained, we're referring specifically to the system. If we take into consideration the surroundings, because the energy of the universe is constant, the effect on the surroundings is the opposite in each case. Okay, and that's why processes like melting and vaporization and sublimation are often referred to as cooling processes, and this is because they are removing heat from the surroundings and adding it into the system in order to cause these phase changes to take place. On the other side, we have condensation, deposition, and freezing, which are often referred to as warming processes, and this is because as the system loses energy, that energy is released from the system into the surroundings, causing the surroundings to warm up. And this is the reason why when you walk into a sauna, for example, where there's a lot of steam in the air, and that water vapor then condenses onto your body, it feels like a warming event, and that's because energy is being lost from the water and that's being transferred onto you, and so you experience it as warming. On the opposite side, when you perspire, right, your body does that in order to cool the body off, and that takes place because heat is transferred from your body to your sweat, and that's what causes the sweat to vaporize, cooling your body, which would be considered the surroundings in that instance. Now, for each of these specific phase transitions, there is an energy that's associated with the transition. Now, these values that we are looking at here are specific for water and for these specific phase transitions. To do this, we will once again use our sign for an enthalpy change, and we will add a little subscript indicating the process that this phase change is describing. So for example, here, delta H of fusion, where fusion is the process of going from liquid water to ice. Now, depending on the direction that we're going, this sign can be either positive or negative. Okay, if we're going from ice to liquid, that's going to be a positive energy change because that's an endothermic process, and it has a value of 6.01 kilojoules per mole, meaning that it requires 6.01 kilojoules of energy to melt 1 mole of ice. To go from a liquid to a vapor, once again, that's an endothermic process. This time we're using the subscript vaporization. Okay, and that has an energy of 40.67 kilojoules per mole. Okay, once again, meaning that it requires 40.67 kilojoules in order to vaporize or evaporate 1 mole of liquid water. Now, the important thing is that these values apply for the phase transition taking place if we've already changed the temperature to the transition temperature. So in other words, the energy value here does not include any changes in temperature. That's merely for changing the phase of the material from, for example, a liquid to a vapor. Does not take into consideration any temperature changes that might be taking place. So we'll have to worry about those separately. Okay. Because enthalpy is a state function, you'll notice that the process of going back from a vapor to a liquid is the same number, has the same magnitude, just the opposite sign. So typically you will only see delta H of vaporization and delta H of fusion tabulated, and you're expected to recognize that for the opposite processes, all that you do is change the sign on the number. Now, if we want to get quantitative, we can use the molar heat of fusion or the molar heat of vaporization or the enthalpy of vaporization in order to calculate the amount of heat required to make these phase changes happen using the equation Q is equal to the number of moles multiplied by the enthalpy of fusion or the molar heat of fusion, okay? Or Q is equal to N times the enthalpy of vaporization. So as we look at this equation, it's important to recognize what each of the variables represents. So if we look at Q, Q represents the amount of heat transferred. N represents the number of moles that we want to convert from the solid phase into the liquid phase. And delta H of fusion tells us the amount of energy required to convert 1 mole of that material from the solid phase into the liquid phase. These work if you prefer to use equations. However, if we understand what these values represent, we can also just use them as conversion factors as you did last quarter with things like density and other properties. So let's take a look at how we would do this. So let's calculate the energy required to convert 5 grams of water at 100 degrees Celsius to vapor at 100 degrees Celsius, making use of the fact that the enthalpy of vaporization is 40.67 kilojoules per mole. So one option is to use the equation that we saw on the last slide, where Q N times delta H of vaporization. So that would be equal to the number of moles. So the first thing I would need to do is determine the number of moles. So we could convert 5.0 grams using the fact that 1 mole of water is equal to 18.015 grams. Okay, and so that allows us to calculate that we have 0.2775 moles of water. Okay, so we now plug this in for N in the equation above. So we have 0.2775 moles multiplied by 40.67 kilojoules per mole. Okay, and if we do that, I'm going to erase this bit down here real quick. We get that that's equal to 11.29 kilojoules, or based on our significant figures, that's just 11 kilojoules. Now, one thing you'll notice as I'm doing these calculations is whatever operation I'm doing on the numbers, I also have to do on the unit. So I'm multiplying my units together. As a result, moles will cancel, and that leaves me with just the units of kilojoules. Now again, if I don't want to have to memorize this equation, what I can do instead is simply do dimensional analysis. So once again, we can just start with our 5.0 grams of water. Okay, and convert into moles just like we did previously using our formula weight. So we have 18.015 grams per 1 mole. All right, and now my next conversion is going to simply make use of this value. So I will have 1 mole in my denominator so that my units work out, and then in the numerator I'll get 40.67 kilojoules. Okay, and once again I'll just multiply what's on the top, divide what's on the bottom, and I get the exact same answer of 11.29 kilojoules. Once again, moles will cancel, grams will cancel. The units that I'm left with are kilojoules. Okay, and then using significant figures, once again, I would just have 11 kilojoules. Let's now take a look at the other part of the heating curve that we looked at, which is the energy involved in changing the temperature of a substance. And to do this, we'll use a property called heat capacity. And there are three slightly different types of heat capacities that we'll look at. They all are the exact same general idea, however, which is simply that the heat capacity is the amount of energy required to raise the temperature of a substance 1 degree Celsius. The first type that we'll look at is molar heat capacity, that's indicated with a lowercase c and then a subscript of P, indicating that it's taking place at constant pressure. And this is the quantity of energy required to raise the temperature of 1 mole of a substance 1 degree Celsius. And again, this is at a constant pressure. For this, we have the equation that Q, or the amount of heat, is equal to the number of moles multiplied by the molar heat capacity multiplied by the change in temperature. And the units for this is, for molar heat capacity, is joules per mole degree Celsius. Now, one thing to make note of, because we're dealing with a change in temperature, it actually doesn't matter if we deal in degrees Celsius or Kelvin, because a change in temperature in degrees Celsius and in Kelvin, those are both the same. So it doesn't actually matter which units we use, as long as we have the temperature in Celsius or Kelvin at both points, at our start and our finish, because it's a change. The other type of heat capacity that you'll commonly encounter is specific heat capacity, or just specific heat, which is given the symbol lowercase c with a subscript of S. And this is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius, once again at a constant pressure. And this has the equation Q is equal to the mass multiplied by the specific heat capacity times the change in temperature. In this case, the specific heat capacity has units of joules per gram degree Celsius, once again, so that if we put that in, if we look at our units, we'll have grams here for the mass, and then degrees Celsius for temperature, and the units that we'll be left with for heat will just be joules. The final type of heat capacity that we encounter is just referred to as simply heat capacity, and it's given the symbol capital C with a subscript of P, once again for constant pressure. And this is the most generic. This is simply the quantity of energy needed to raise the temperature of an object by 1 degree Celsius. Okay, in this case, it doesn't matter if we're dealing with moles or grams or whatever, because it's just an object, whatever it is. Okay, and this is referred to as an extensive property, whereas the other two are both what we call intensive properties. There we go. For intensive properties, the amount of material we have doesn't matter, because we take that into the account with either the moles or the mass. And so we can tabulate a specific value for the molar heat capacity or the specific heat capacity. For just plain heat capacity, where it's an extensive property, now the amount of material that we have matters, okay? And the value that we specify for the heat capacity depends on exactly what we have in front of us. Okay, so for example, let's say that we have a cup of water. We could define an extensive heat capacity for that cup with that specific amount of water in it. Okay, that's the nice thing about the extensive heat capacity values, is you can do mixtures of things, you can do all kinds of different things, but the value that you get is specific for that substance. Okay, in the case of specific heat capacity, CS, it doesn't matter how much water we have, because we will take that into account with the mass. The specific heat value stays the same. In the case of heat capacity, let's go back to that mug of water. If I change the amount of water in that cup, the heat capacity is going to change. Okay, and that's because there's more water. We're now going to require more heat to change the temperature. So once again, if we have intensive properties do not depend on the amount of material. Extensive properties depend on the amount of material present. So here are some examples of molar heat capacities. Again, our units are joules per mole degree Celsius. Okay, and one thing you'll note is if we look at things like water and ethanol, okay, these actually have very high molar heat capacities, meaning it takes a lot of energy to increase the temperature of these materials. If something has a low heat capacity, low molar heat capacity, something like graphite, this means that the temperature is easily changed, or it doesn't take a lot of energy to increase the temperature of that material. All right, let's now take a look at a problem that combines both heat capacity and enthalpy of fusion together. So let's calculate the amount of energy required to convert 237 grams of solid ice at 0 degrees Celsius to hot water at 80 degrees Celsius. Okay, in this case we have two different steps going on. One, we have to melt ice, 237 grams of ice, that's at 0 degrees Celsius, so we have to melt that from a solid to a liquid, and then after we've converted it from a solid to a liquid, then we have to heat the water from 0 degrees Celsius to 80 degrees Celsius. So there's going to be two different steps. We'll just break it into those individual steps, calculate each one individually, and then combine the results together. So the first thing we're going to need to do, we're going to need to convert mass of water into moles of water. Then we're going to need to calculate the energy to convert the solid ice into a liquid. We'll do that using the enthalpy of fusion. And then after that, we will finally heat the water from 0 degrees Celsius to 80 degrees Celsius using the equation that Q is equal to the number of moles times the molar heat capacity times the change in temperature. Okay? And then once we've got those two different energies, we'll just add those together to get the total amount of energy. All right, so first thing we need to do is calculate the number of moles. So again, we can do this using dimensional analysis. We have 237 grams. Okay, there's 18.02 grams of water in 1 mole, so that gives us 13.2 moles of water. Our next step is we're going to calculate the energy required to melt the ice. Okay, so Q1 we said is equal to moles times the enthalpy of fusion. So we said we have 13.2 moles times 6.01 kilojoules per mole. You'll notice moles cancel, leaving us with a value of kilojoules. So this tells us that it's going to require 79.3 kilojoules to melt the 237 grams of water. Our next step then is to calculate the energy that's going to be required to heat the water from 0 degrees Celsius to 80 degrees Celsius. So for this we have Q is equal to the number of moles times the molar heat capacity times the change in temperature. So we have 13.2 moles. The molar heat capacity is 75.3 joules per mole degree Celsius, and the change in temperature is 80 degrees final minus the initial, which is 0.0 degrees Celsius. All right, and if we do the arithmetic, we get a value of 79.5 kilojoules. Now you'll notice, once again, if we look at our units, we have moles on top, moles on the bottom, those will cancel. Degrees on the bottom, degrees Celsius on top, so those will cancel, leaving us with the value of joules. Now, we did a little bit of hocus pocus here because in reality, what we got, if we did the arithmetic, is 79,500 joules. Okay, just be aware that the units here have to match up the units here. All we did is then take that and divide it by 1,000 in order to convert into kilojoules, because down in our next step, we're going to be adding these values together. So we have 79.3 kilojoules plus 79.5 kilojoules, and so we get a total of 158.8 kilojoules. All right, now this still isn't completely right though, because we also need to take into account the number of significant figures that we have. Now, if we take a look, we might be tempted to say we only have 2 significant figures from this number. But if I take this number minus this number, I get 80.0 degrees Celsius. So I still have 3 significant figures, so this is going to round up to 159 kilojoules for my final answer.